Hey guys, welcome to lesson 5.1. Today we are talking about polynomial functions. Let's start with some vocabulary. So a polynomial is defined as a monomial or the sum of monomials. Any real number, a variable, or a product of real numbers and variables with whole number exponents is a monomial. The exponent of the variable, if there is only one variable, or the sum of exponents, if there is more than one variable, is called the degree of the monomial. However, the greatest degree among the monomial terms is how we classify the degree of a polynomial. Now, a polynomial function in the variable x is said to be in standard form if the terms are arranged by degree in descending numerical order. So let's go over a couple things that we've just talked about. So first of all, we talked about the idea of a degree. Now the degree of a polynomial function is essentially the largest exponent that you see when you're looking at the function. So for example, if we had x squared, I'm gonna write this down, if we had x squared plus 3x minus 1. The largest exponent that I see is 2, so this would have a degree of 2. It's whatever the largest exponent in a function is. Now, a polynomial function is said to be in standard form if the exponents are decreasing in value each time. So for example, if we had x to the 5th plus 3x to the 4th minus 3x cubed plus 7, notice how my powers are decreasing each time. So if we are in numerical order from greatest to least in terms of the exponents, then that function is said to be in standard form. So let's go ahead and move on to the next part here. So a polynomial, p of x, where n is a non-negative integer and all of these a sub n up to a sub 0 are real numbers, this is generally what the format is going to look like for those functions. Now, a point where the graph of a function changes direction from upwards to downwards or from downwards to upwards is called a turning point. Oops, already has the word point there, so I don't need to write it again. And the direction of the graph of a function as you move from left to right away from the origin is commonly called the end behavior. Okay, so a bunch of vocab words that we're going to be referring to today. Let's go ahead and talk about how these work. So first of all, I would like to classify some polynomials for you today. So we're going to classify polynomials in two different ways. We're going to classify them by degree, or the highest exponent in the function, and we're also going to classify them by number of terms. So let's go ahead and look at the first part where we classify by degree. So what if your polynomial has a degree of 0? Well, that would tell you that you are looking at a constant, okay? And we know that a constant is some number that doesn't have a variable attached to it. For example, like -7. So if you see -7, obviously no variables attached to it, so it is just going to be a constant. Now, number 1, so if we have a degree of 1, that is going to be a linear function, okay? So if a degree is 1, it might look something like this, 2x plus 5. So notice how the highest exponent is 1, so that means that you are looking at a linear function. Now, what if your degree is 2? So in other words, if your highest exponent is 2, that is going to be a quadratic. And an example of a quadratic might be, I don't know, x squared minus 3x plus 4. So the highest exponent is 2, and that makes it a quadratic. The third one, so if we have a degree of 3, that is going to be considered a cubic function. So for example, we might have 5x cubed minus 4x. Anything that the highest degree is 3 is going to be considered a cubic. All right, what about a fourth degree? A fourth degree is a quartic polynomial function. Okay, and a quartic function might look like this, x to the 4th plus 3x squared minus 1. The highest degree is a 4. Last but not least, let's look at a degree of 5. A quintic function is what we name a degree of 5. And a degree of 5 might look like this, x to the 5th minus x squared plus x plus 7. But obviously, there could be a number of different ones. That's just any old example that I could think of. Now, what if we have a degree that's greater than 5? Anything that's greater than 5 is going to follow this rule. So let's say we have a degree of n. It could be anything, 70, 100, 1 million. Any degree that's higher than 5 is going to be considered an nth degree. Okay, so after 5, we don't have any more fancy names. We just call it an nth degree. So for example, if we had x to the 8th minus 3x to the 4th plus 2x minus 1, the degree here is 8. So we're just going to refer to this as an 8th degree. And that is how we classify polynomials by the degree. Okay, let's go ahead and move on to the next page. So next page, now we're going to classify polynomials by the number of terms. So what if a polynomial only has one term? Well, the special name we refer to that as is a monomial. So a monomial is an expression that just has one term. So for example, maybe 8x cubed. Okay, only one term. We don't have multiple terms. Nothing is being added or subtracted to this term. What if we have two terms? We refer to that as a binomial. So an example of a binomial might be x squared minus 8x. Notice how there are two terms. What if we have three terms? This is referred to as a trinomial. And again, a trinomial has three terms. So for example, maybe x squared plus 10x plus 25. Last but not least, let's look at a fourth term. So what if we have four terms? This is referred to as a polynomial. So just like we said before with the nth degrees, once we get beyond 4 here, we don't have any special names anymore. We're just going to use the term polynomial. So if your expression has 500 terms in it, we refer to it as a polynomial. The only number of terms that have special names is one term, two terms, or three terms. Anything beyond that is just considered a polynomial. So an example of something with four terms might be x cubed minus 2x squared plus x plus 4. Okay, and like I said, anything beyond that is still going to be considered a polynomial. Let's go down to the first example of what we're going to have today. So the first type of example we're talking about is example number 1. We are going to write each polynomial in standard form. Remember, we said standard form is when you have the highest exponent first, and then you go down in number order. Then we're going to name the polynomial by degree and number of terms. Let's look at part A. So we have 4x squared minus 3x plus 5x to the 4th. Well, if I'm going to write this in standard form, my highest exponent needs to go first. So I'm going to put 5x to the 4th first, and then I'm going to go down from greatest to least. So the next highest exponent is going to be 4x squared. So I put plus 4x squared, and my smallest exponent is negative 3x. So now this is in standard form because we are going down numerically. Okay, so now I'm going to classify this by number of terms and the degree. Well, I notice that my degree here is 4. Okay, that's the highest exponent in my function. So I'm going to label that. Hey, that's my degree. And so we know that a fourth degree, if we look at the previous page, a fourth degree is referred to as a quartic. So the first thing we're going to put down is quartic. This is a quartic function. And then now we're going to classify this by the number of terms. Well, I notice that this has 3 terms. So that means I'm looking at 3 terms up here, which is a trinomial. So this expression is named a quartic trinomial. Okay, it has a degree of 4, and it has 3 terms, making it a quartic trinomial. Let's look at part B. We have 2 plus x cubed minus 3x squared plus 7x. Let's go ahead and write this in standard form first. I notice that my biggest exponent is going to be x cubed, so I put x cubed first. My next biggest one is x squared, so negative 3x squared. Then I have plus 7x until I get to the degree of 0, which is just the constant, or plus 2. So my degree here is 3. And if my degree is 3, that is going to make this let's look at that previous page. Oh, look at that, a cubic function. So if our degree is 3, this is going to be a cubic. And then also, this has 1, 2, 3, 4 terms. And like we said, anything that is greater than 3 terms is going to be referred to as a polynomial. So this is a cubic polynomial. All right. Part C, we have 8 plus 3x. Let's go ahead and put this in standard form. Let's look for my highest exponent. Well, here I have a constant and a 3x. I know that this 3x has a degree of 1, so my highest degree is going to be 3x, and then I have plus 8. Okay, so since my degree here is just 1, right? I don't have any special exponents or anything like that. That's going to make this a linear function, because this forms a straight line if we were to graph it. And since this has 2 terms, this is a binomial. So this is referred to as a linear binomial. Last but not least, part D, we have x to the 7th. Notice how we have a 7th degree. Like we said before, whenever we get above 5 for degrees, we're just going to refer to that as an nth degree. So this is going to be referred to as a 7th degree. So this is a 7th degree. And since I only have 1 term, this is going to be referred to as a monomial. So this is a 7th degree monomial. And that is how you classify a polynomial based on its degree and its number of terms. All right, let's go ahead and move it down to the next part, which is end behavior of a polynomial. So the degree of a polynomial affects the shape of its graph and determines the maximum number of turning points. It also affects the end behavior of a function. So what we're going to do is we're going to look at the end behavior of even functions and odd functions. And we're also going to talk about how many turning points that those graphs are going to have. So let's look at even functions first. Now, when you think about even functions, I want you to consider x squared because that's familiar to us. Now, we know that x squared looks something like this. It's the shape of a parabola. Notice how it's going up on the left-hand side and up on the right-hand side. So even functions are all going to follow this structure. As long as the leading coefficient is positive, so if we have a positive number in front of that even exponent, that means that your function is gonna face upwards. So let's take a look at y equals x to the 4th minus 3x cubed plus 4x. Well, something I want you to notice about the graph of this function is that as we go towards the left, your function is going upwards. And the way we're going to write that is we're going to say as x is approaching negative infinity, f of x is approaching positive infinity. Okay, so as we're going to the left, the graph is going upwards to positive infinity. Now on the right-hand side, we notice that same exact thing. As we're going to the right, the graph is approaching positive infinity. So the way we're going to write this is we're going to say as x approaches positive infinity, or as we go to the right, the graph, f of x, is also approaching positive infinity. Or in other words, the y value is going up and up and up to positive infinity. Okay? Now let's talk about the number of turns that this graph is going to have. So a little trick that I want you to use for the turns of the graph is that your turns are going to be 1 less than your degree. Okay, so if your degree is 4, that means that your graph is going to have 3 turns. And those are just a couple of key things to look at when we have even functions. Now let's look at a negative even function. So what if we have y equals negative x squared plus 4x? Well, this negative right here tells me that our graph is going to now face downward because we know if we have negative x squared, our graph faces downward. So the same is true for any even function. So this is the opposite of what we were looking at before. So as we go to the left, we are approaching negative infinity. And as we go to the right, we are also approaching negative infinity. So we're going to write that down as x approaches negative infinity, then f of x also approaches negative infinity. And when x approaches positive infinity, f of x approaches negative infinity. Okay, so the number of turns that this graph has is 1 less than the degree. So since the degree is 2, that means that this graph has 1 turn. Okay, now let's look at odd functions. So when you think of odd functions, I want you to think of, for example, x to the 1st. Okay, so we know x to the 1st, that is just any old linear function. So we might have a line that looks something like this. So we have a positive leading coefficient and our graph is going upwards in the positive direction. So this is true for all odd functions. So as long as you have a positive leading coefficient, your graph is going to be going down on the left-hand side and up on the right-hand side. Okay, so this holds true for every single odd function. So let's go ahead and look at y equals x cubed minus 2x. So first of all, let's look at the graph here. As we go towards the left, notice how your graph is approaching negative infinity. As we go to the right, notice how your graph is approaching positive infinity. So even though your degree is 3 now, it still follows the same general direction as a regular linear function. It goes down on the left and up on the right. So what we're saying mathematically is as x approaches negative infinity, f of x is also approaching negative infinity, but as x approaches positive infinity, f of x also approaches positive infinity. Or in other words, we're going down on the left and up on the right. And the number of terms that this has is going to be 1 less than the degree. Since the degree is 3, this graph has 2 turns. Last but not least, let's look at a negative leading coefficient. So what if we had an odd function that has a negative leading coefficient, like negative 0.5x cubed plus 4x plus 1? Well, if you take a look at this graph, it's just flipped from the other graph. So as we go to the left, your graph is approaching positive infinity. As we go to the right, your graph is approaching negative infinity. So mathematically, the way we're going to write this is as x approaches negative infinity, f of x approaches positive infinity, and as x approaches positive infinity, f of x approaches negative infinity. And this graph is going to have 2 turns because the number of terms is 1 less than the degree. So to wrap it all up, even functions are going to go either up in both directions or down in both directions, depending on if your leading coefficient is positive or negative. For odd functions, if you have a positive leading coefficient, your graph is going to be going down on the left and up on the right. And if you have a negative leading coefficient, it's going to do the reverse, up on the left and down on the right. So always think of your 2 common functions that you remember from everyday life. We have x squared that resembles a parabola. All even functions are going to resemble that same end behavior as well. And then odd functions, think of x to the first. All of your odd functions are going to also resemble the end behavior of just a regular line graph. Let's go ahead and move on to the next page. So we're going to use what we just learned. Oh, excuse me. Totally didn't erase this. We're going to use what we just learned to go ahead and describe the end behavior and try to transfer it down to a graph. So let me go ahead and erase this real quick. Awesome. So the first thing I want you to do is we are going to analyze the function. And we're going to figure out everything we have going on and how we can actually graph this thing. So the first thing that I always want you to analyze is your degree. So my degree here is 3, which means that this is going to be an odd function. Okay, so it's going to go up in one direction and down in the other. The second thing I want you to notice about the function is the leading coefficient. Now, the leading coefficient here is a negative leading coefficient, and that is negative 4. So the leading coefficient here is negative 4. Now, since we have a leading coefficient that's negative and we have a degree that's odd, remember that this is going to do the reverse of the x to the first graph, which goes uphill. Since this is negative, this is going to go downhill. So we're going to be going up on the left and down on the right. Okay, so let's go ahead and draw generally what's going to be happening here. Okay, another thing we can say about this is we can say, well, since the degree is 3, this graph is going to have 2 turns. And then last but not least, since our degree is 3, that means we're going to have at most 3 real zeros. The number of zeros that are real is going to be at most whatever the degree is. Now, the second thing I want you to do is we're going to create a table of values just to kind of give us an idea of where this function is going. So the first point that I'm going to plot is just something easy. Let's go ahead and plot -1. So if we plug -1 into this function, our output is going to be 13. Then we can plug in 0. So if we plug 0 into this function, obviously these would both turn into 0, and that would be +7. Now if we plugged +1 in, that would be -4 times 1 cubed plus 2 times 1 squared plus 7. That would give us an answer of 5. So let's go ahead and plot those points on our graph. So we have -1, 13, 0, 7, and 1, 5. Now, like we said before, this is a negative odd function, so it's going to be going up on the left and down on the right. So I can just draw my graph going upwards on the left and downwards on the right. Doesn't have to be perfect. We're just kind of drawing the general end behavior here. All right. And now we're going to use the rest of what we got to fill in the blanks. While I know that this is going to have at most 2 turns. So I'm just going down. I might turn here. Oops. This is, of course, acting a little weird. And then that's generally what my graph is going to look like. So I'm connecting the dots, recognizing that I might have 2 turns, and at most I'm going to have 3 real zeros. But the main thing to remember here is that on the left-hand side, we're going up. On the right-hand side, we're going down. So remembering that end behavior is going to be very important. All right, let's go down to example 3. So we're going to graph some cubic functions. First of all, let's graph y equals x cubed minus 1. So something I want you to recognize here is that the parent function of this is going to be y equals x cubed. Okay, so we know the graph of y equals x cubed. Since that's an odd function, it's going to be going up in one direction and down in the other direction. And we also know that if we have the general parent graph, y equals x cubed minus 1 is just going to essentially be shifted down 1 from the parent function. So I'm going to say, hey, that is shifted down 1 from the parent function because -1 on the outside tells us we have a vertical shift. All right, let's go ahead and plot some points just so that we can get an idea of what's happening here. So I'm going to go ahead and plot some points for y equals x cubed minus 1. So let's go ahead and plot -1. Well, if I plug -1 into that function, that's going to give me -2 for a result. So -1, -2 is a point. If I plug in 0, that's going to be 0 cubed minus 1, which is -1. So 0, -1. And then if I plot 1, this is going to be 1 cubed minus 1, which is just 0. Okay, we know that since this is an odd and a positive function, so I'm going to say odd and my LC, leading coefficient, is positive. That means I'm going to be going uphill or up on the right and down on the left. So the general graph of x cubed minus 1 is going to be going uphill on the right and then downhill on the left. And that is what my graph is going to look like. Now let's look at example number 4. We have y equals -x cubed plus 2x squared minus x minus 2. So first of all, I want you to notice that we have an odd function because our exponent is 3. And we also have a leading coefficient that is negative. So since the leading coefficient is negative, that means that my graph is going to be going downhill. So on the right-hand side, it's going to go to -infinity. On the left-hand side, it's going to +infinity, okay? So it goes up on the left, starts high, and ends low down on the right. Or in other words, going downhill. So let's go ahead and plot some points so we can draw this graph. So I'm going to create a table here, x and y. So first point that's super easy to plot is just going to be -1. Now, if I plug -1 into that function, I'm just going to use a calculator. My result is going to be 2. So -1, 2 is a point. Let's plot a few more. So what about 0? Well, if we plug 0 in, our output's going to be -2. So 0, -2. Let's plug in 1. So if we plug 1 in, our output is going to be -2 as well. And then the last thing, if we plug in 2, our output is going to be -4. Okay, so just plugging in enough points to see generally what is happening with this graph. Okay, so like we said before, this is going downhill. So on the right-hand side, we're going down. On the left-hand side, we're going up. And then we're just going to connect the dots with kind of a smooth curve. So our graph is going to go through those 2 points. And notice how it just kind of flattens out right here. And then we're going back down. All right, so that is what my graph is going to look like. And every one of these looks a little bit different. So x cubed minus 1 is definitely going to look different than this graph right here. Okay, but like I said, the important stuff to remember is the end behavior and recognizing what the degree and what the leading coefficient does to it. All right, let's go ahead and move on to the next page. This is using differences to determine the degree. So example number 5, we're going to use the table below to determine the degree of a polynomial. Now the process that we're going to use is a little funky, a little weird, but I want you to follow along as best you can. Pause the video, rewind the video, do what you got to do to understand kind of what's happening here. So if we are using a table to determine the degree, the first thing I want you to do is we're going to say y equals, and then I'm going to put down all of my y values with a little space in between them. And this will make sense in a second. So first I'm going to write down 23, then I'm going to leave a space and put -16. Then leave a space, put -15. And I'm going to keep going until I have all of my y values written down. So what we're going to do here is we're going to look for some patterns. So I'm going to start by using the color blue. So what I want to discover is what is the difference between these numbers? Or in other words, how do I get from this number to this number? And I'm going to figure out what that difference is for each of these numbers. Okay? So to get from 23 to -16, I have to subtract 39. To get from -16 to -15, I have to add 1. To get from -15 to -10, I have to add 5. To get from -10 to -13, I have to subtract 3. From -13 to -12, I am adding 1. To get from -12 to +29, I am adding 41. Okay? So that's how I got from one of these y values to the next y value. And I'm going to refer to the blue numbers as the first difference. Okay? So all the differences between the numbers, that constitutes the first difference. Let's go ahead and do it again with a different color. So now I'm going to move down to these numbers, the blue numbers. Let's find the differences between them. So to get from -39 to +1, I have to add 40. To get from +1 to +5, I have to add 4. To get from 5 to -3, I have to subtract 8. From -3 to 1, I have to add 4. To get from 1 to 41, I'm adding 40. And that's going to constitute the second difference. Let's go ahead and do this again using even another color. So let's go ahead and figure out what we have to do here. So to get from 40 to 4, I have to subtract 36. To get from 4 to -8, I have to subtract 12. To get from -8 to +4, I have to add 12. To get from 4 to 40, I'm adding 36. This constitutes your third difference. So each time we find the differences between those numbers, we are adding another difference. So now we are on the third difference. Let's go ahead and do it again. I'm going to use, running out of colors here. Let me use purple. So to get from -36 to -12, I have to add 24. To get from -12 to +12, I have to add 24. To get from +12 to +36, I have to add 24. Notice how each of those numbers is the same. That's very important. I want you to think about that real quick. That's extremely important. And this constitutes the fourth difference. Okay, so something I want you to draw a connection with right here. Since the fourth difference are the same, so each of those differences are the same. So since the fourth differences are the same, okay, they're all 24. Whoa, look at that. That's probably important. The values in the table represent a quartic polynomial. And you're like, well, what on earth does that word mean? We've talked about that on the first page today. A quartic polynomial is a fourth degree. So what this is saying is, whatever difference you find has the same numbers. So since we went to the fourth difference and we all got 24, that means that your table represents a fourth degree polynomial, and we call that a quartic polynomial in mathematics. So you're going through the pattern, figuring out what the differences are, and then once you figure out, oh, hey, I get the same number, whatever number difference that is, that's going to be your degree of your polynomial function. So that is how we figure out, well, given this table, what is the degree of the polynomial? We use the common differences, and whatever difference we're on, that is going to be our degree, or in other words, our highest exponent. All right, guys, that concludes 5.1. Thanks for tuning in. Make sure you do your homework, and I will see you back here next time.